So we have seen, you know, several ways to which you can determine the convergence or the divergence of sequences. One thing that you already observed is that there is no one settled way to basically know in a decisive manner that, if you have been given a sequence, whether it converges or diverges. This always depend on, it's like you have to always imply something without the nature of one of the suitable results that you basically learned was sandwiching principle. Your sequences sitting between two convergent sequences. You know their limits. Then that sequence that is sitting between your limits, the two sequences, is going to converge to basically the same limit. Also saw what we call the monotone convergence theorem. So that if we have a monotonic sequence which is bounded, that it must converge at. So we know that it converges to what? It converges to what? It converges to supremum or infimum, depending on whether the sequence is decreasing and bounded above or decreasing or bounded lower. Okay. Then we did another result, which was bounded monotonic convergence theorem. Here are maybe Versus theorem, Versus theorem, which says that if a sequence is bounded, then that sequence contains a convergence subsequence. Okay. So we saw several things. But you can see that in all these convergence results, we know that, especially monotone convergence theorem or sandwich rule, we know that the sequence is converging to what? We know the limit. So there is going to be the limit, which is going to be the limit shared by smaller or bigger sequence in sandwich principle. But sometimes we are not interested in knowing that whether a sequence converges. So it's like sometimes we are not interested in the limit of basically the sequence, but we are interested in that, yes, it's sufficient for us that it is converted. So today we're going to see some of things which are going to tell us that basically we can have some kind of convergent sequences whose limit we don't know. And it's fine to know these details sometimes. But at least the criteria that we are going to discuss today is going to guarantee that the given sequence is a convergent sequence at all. That's what. Now, I will talk about what we mean by the Cacuhy sequence. Cacuhy sequence. There is a Cacuhy sequence. So imagine the sequence of linear space. Each space R. Imagine I have a space and I have a sequence I. this sequence has a very interesting property that after an instant, all of the terms of sequences are kind of logged into the walls. All terms of in other words, after some instant, all of the terms of the sequence are going to have the distance between them is going to be less than the radius or the distance of the radius. And we're not doing the abstract result, but there can be sequences in which such kind of sequences, just think about it. I have this ball, okay, which has certain radius, but I can shrink it as much as I want. And I can shrink it that way that everything basically gets closer to something very specific. We can say such kind of sequences as the Cacuhy sequences. The Cacuhy sequences are what? These are the sequences which after a certain instant, their all terms are basically sitting within a ball. So we don't know that it is going to converge to what? Are they going to be convergent or not? Okay. We cannot see that. I mean, if we have Cacuhy sequences, it must be and see that it's also other way around. I mean, can you see that if you have a convergent sequence, it must be Cacuhy actually, because in the convergent sequence, something similar is happening already. Like you have a limit, and you know, all points of the basically sequence are just bunching up around that particular point. While here you don't have a fixed point actually. You just say that all terms of the sequences are basically kind of at a smaller distance than a fixed distance. We're going to call such sequences as Cacuhy sequences. These are going to be very interesting sequences. So, what do you think that how should we define it? I mean, the situation that I explained, what should be the definition of a sequence to Cacuhy? So, we're going to say that a sequence, okay, the N is Cacuhy sequence. If for epsilon positive, what happens?
AI minus AKI.
So for every epsilon positive, there exists an instant. And okay, such that after that instant, like after that instant, I'll write something here. You take any two terms, like after that instant, you take any two instants, like n and m are any two instants after this fixed instant. The distance between xn and xm should be less than 1.
Bn minus
Bn minus because I have written this in here. Bn. Right? Is it making sense that it is same thing that basically I just described? That what is the key difference between both? Between the convergence and here. So here you don't have a specific point, okay, to which you say that all terms of the sequence are going to be in the neighborhood of that point. We are saying that sequence of Cacuhy, if you fix an epsilon positive, okay, a time will come that after that time you take any two instant, okay, or any two terms of the sequences, the distance between those two terms is going to be always smaller than epsilon. In other words, a sequence of Cacuhy which is wandering around, So it is really Cauchy. You draw a ball basically of epsilon anywhere you want. Then after some instant, all of the terms are going to basically kind of sucked into this ball. It's never going to leave basically. This. Okay. Okay. So you need to keep one key difference between your that here the ball is not around specifically. We're saying that the distance between all terms is going to be after that instance smaller than 1 second. You choose any two terms. I can see where what is it. इसका मतलब ये है इसको अगर मैं और आसानी से कहूँ so you know the description is going to be that after this instant which is L all terms are going to be kind of always stay in a ball of the radius epsilon. So that's what we are saying. So that could be centered. That is going to be eventually centered because we know or we are going to prove that the Cauchy sequences are convergent. If they are convergent, they will be bunching around that point. But at the moment, we don't know that the Cauchy sequences are convergent. But this calculation is saying that after this instant n, all terms are going to stay at a distance at most epsilon. Not even at most, actually. It's going to be strictly smaller than.
It's not radius.
It's. It's not like radius actually. If you fix, for example, one of the index, yes, then it is radius. But if it is already, arbitrary and an m are arbitrary, we're not going to say that it's a radius, but we're going to say that the distance between any Pn and any Pn is going to be always smaller than epsilon. And hence you can, interpret it as that you have some ball, centered somewhere, and all terms are falling in that. Now, what is that something? No, I don't know that. That's something. We can talk about that. It's not the case. Okay?
And in other words, can you say we cannot separate?
We cannot
separate after a section. We cannot separate the terms.
We are going to get from this.
Then, they are getting. That's not.
So it's like, I can choose epsilon as much as I want. So it's like, if the sequence is Cauchy sequence, no matter how small epsilon I choose, all terms are going to fall into this sequence. Anyway, you can have lots of issues for it. That's a good example. Imagine I have a sequence. A and minus n over n. Alternated sequence. My claim is that this is the Cauchy sequence. So for given epsilon, I have to find such a capital. That's what. What we need to do, I need to take basically the difference A and L.
Yes, sir.
That will be equal to minus 1 raised to plus or minus 1 raised to minus 1 0. I have minus 1 0. That will be minus 1 raised to n and minus 1 over. Can we say that this number, whatever this number is going to be less than or equal to 1 over n plus 1 over n? Can't go beyond this one. And one of the things that one of the things that we can immediately observe is that these n and m are arbitrary natural numbers after n. So by trichotomy law, one of them must be bigger than or equal to another. Okay. So let's assume without loss of generality that n is bigger than. So if it is bigger than m, can you give me upper bound on basic and conditional?
N plus x.
Less than, strictly less than 2 upon n. Why? Because 1 over n is less than 1 over m, and you add 1 over m on both sides, so you're going to have 2 over m. Okay? Are you getting the point? And what does it mean? It means that if we reduce from here, then it's a Cauchy sequence.
Yes, I do it.
So it means that
Instead I get those alone.
it's like it's something which you can choose as much as small. So as m will get bigger, this will get smaller and smaller and smaller. It's kind of okay. So I can choose arbitrary epsilon and I can find a capital N for that, right? But it is sufficient to show that the distance between two terms is arbitrarily small actually. So if it is arbitrarily small, it is equivalent to what you have. Because ये भी क्या है? This is representing the distance between Pn and Pm is arbitrarily small actually. So I can make it small as much as I want. That's what I did. Definition is small. Satisfactory. Restrict कैसे पता है? That's something like this. What will be the guess for your? What will be your guess for this? This was, if I say, this was instantly. We don't need instant here at the moment. Why? Because we haven't chosen arbitrary epsilon. So if we choose arbitrary epsilon, if we make this less than arbitrary epsilon and as we solve inequality, okay, then we can find basically capital F. So at the moment I'm just giving a generic argument. So I can make this distance as much as small I want.
We can take it 2 over m is equal to epsilon, and from that we can use this.
Then we can take arbitrary epsilon. So like if you just put arbitrary epsilon here and solve inequality, and that basically get epsilon in the terms of. And then that is going to give you. Anyway, so essentially point is that I can make these after some instant, as much as smaller I want it. Okay. We'll do more examples. But let's move to a small example. That every convergent sequence is Cauchy. You think that every convergent sequence should be Cauchy? Because it trivially satisfies this definition. So you have a fixed point and all terms are in that basically. All terms are going to be at a at a fixed, so it's like all terms of the sequence from a fixed point are going to be less than basically what else. But what we have to do that we have to drive the definition of Cauchy sequence from convergence set. We want to show this regression. So intuitively it looks like it's okay. We can make it up. So if we say that let Pn be a sequence, let Pn be a sequence with convergence to P as n goes to infinity. Okay. What does this immediately is giving me?
Pn minus P.
So this is going to be given here that if I given epsilon positive, there exists capital N such that so Pn minus P is less than epsilon. I mean, you can also see that I can very easily prove this result in music spaces as well. So this distance is going to be just a Pn of this. For all n bigger than or equal. ठीक है ठीक है so choose any n and m bigger than or equal to n. Choose any n and m bigger than. So it's like this n is arbitrary. So I can put k here or anything, and I'm choosing any two arbitrary values. So this n is not necessarily same as this small. I'm getting the point. This is the generic statement. If you wish, you can put k here and k here, and then I can say that let's choose that any two elements. And our objective is to show that the distance between Pn and Pm should be less than 0. So think about the distance between Pn and. What is your guess? I'm going to correct you here. So that Pn minus P plus P minus Pn. This is less than or equal to Pn minus P plus P minus.
Twice 10. That's one. Twice 10.
I'm waiting for that moment. That would be nice. Alright. So since this n is after this n, so this inequality must be true for it. And since this m is after this m, so the same inequality is also going to be true for Pm. So the inequality, this inequality is true for both expressions. We're going to say that okay, this is less than epsilon by 2 plus epsilon by 2, which is epsilon. Every convergent sequence is Gaussian. We can also see that. Now, let's see some examples which are not Gaussian. We have some examples which are Gaussian. You can have also examples which are not Gaussian. Example, one of the interesting examples is that Sn is a sequence which is sum of A equal to extend to 1 over here. It's like 1 plus 1 over 3. And you take the sum of these terms up to the. So that and my claim is that this is
Sequence of partials.
yeah partial. So it's like so that's 1 plus 1/2 plus 6 plus 1 over 5. This expression. So my claim is that this is not a partial sequence. In other words, you take any two arbitrary terms, you can't make them close as much as you want. For example, here we were able to make them close as much as we want. But here we will see that this is not possible. So what we need to do, what would be the Sn minus Sm actually? M and N are any arbitrary terms. Okay, take a particular M equals to what? 2n. You see this. So if a sequence is Cauchy, this claim must be true for any chosen M and M. So if it is not true for any particular two M and M, the sequence is not Cauchy. So I'm saying that, okay, choose n and this basically m. So the outcome is going to be
Sn minus.
so Sm
X from delta, what about k minus 2 times?
इधर इधर m रख दें इधर m रख दें इधर ओके ना ठीक है
What about this?
so it's going to start from there so it's going to start from 1 over
Q.
n plus 1 up to 1 over 2n because the so it's like that is going to be the sum from 1 to from 1 over 2n and you are subtracting basically from 1 to 1 over n and so you are remaining with basically ठीक है अच्छा for this can I say
Q.
जी बोले फल नहीं आएगा अच्छा what would be s to n so it's going to be 1 plus 1 half plus 1 third plus 1 over 2n so you went you read all the way to 2n but बीच में कहीं 1 over n भी तो होता and then you will have 1 over n plus 1 and so on. We are saying that our S2n is this, okay, and we are subtracting this part out of it. Now, if I compare this each of expression with 1 over 2n, then which number is greater? Is 1 over 2n is bigger or 1 over n plus 1 is bigger?
1 over n plus 1 is bigger. N plus 1.
1 over n plus 1. The more smaller denominator you have, the more bigger number is going to be. Okay? So I will say that this number is bigger than 1 over 2n. The next number is also bigger than 1 over 2n. In fact, in this sum, all of the terms are bigger than 1 over 2n. So I would say that this should be equal to this guy should be equal to what? This guy should be bigger than, we write it directly here. It's going to be bigger than 1 over 2n. This term is bigger than 1 over 2n plus 1 over 2n. The next term is also going to be bigger than 1 over 2n and hence plus 1 over. Agree? In this sum, each term is bigger than 1 over 2. So this total sum is going to be, it is going to be 1 half. Agree? So what we showed that if I take the distance between 2n terms and nth terms, it's always going to be bigger than 1 half, no matter what n you choose. No matter how big or small n you choose, okay, this distance is always going to be bigger than 1. So you can't make it less than epsilon, no matter how hard you try it.
For every epsilon you can't make it.
Huh?
For every epsilon you can't make
For
it.
every epsilon.
But there will be some epsilons for which you can.
Obviously, one should be. If it is less than 1 half, bigger than 1 half, so in other words, you can't make these two terms arbitrarily close with each other. So you're going to say that that's not the classic. To make it. There are more examples. Yes, it is going to basically slowly diverge out. Though it's going to take loads of time, we can show that eventually this is going to be. So can you see that, what will be the good thing, goodness of this result is, if a sequence is not Kashi, forget about it, it's not going to be the result. ठीक है Let's move ahead. So I would like to move to a bigger result basically. That result is what we call the completeness of the real learning. Okay. Completeness of real learning. What do you mean by that? I mean, if you see that Slogan book,